Yeah, I thought I'll once in a while prepare again some nice survey. Uh, we might have 100% current participation, so there's nobody on the live stream this time. Maybe people still come. I've not been really a good boy with starting on time. But let's start. This last section in this part is a little bit of an outlier, if you want, in that it's a totally different problem. It doesn't blend as well into the other topics where the choice of problems and example algorithms was more to demonstrate specific techniques that hopefully you can generalize to other problems. This one's maybe a bit different, but I kind of felt you cannot talk about approximation algorithms and not show this one. It's a beautiful algorithm and also has a good story around it. In the next section, we'll look at Christophidis' algorithm for the traveling salesman problem. It's a very well-known approximation algorithm. It's both very simple, also ingenious in a way to use the right ingredients. And it's for a very long time, it used to be the best we know about this problem in terms of approximation. And so it's well worth seeing. If you're learning about approximation algorithms, I think you're supposed to know this one, even though it might be harder to generalize the techniques used there to other problems. The problem that we're looking at is the metric traveling salesperson problem. And let me stress that metric is really crucial here. Metric means that the distances between the points obey the triangle inequality. That's all it says. But in general, if you give me an arbitrary TSP instance, who knows what the distances might be like. And in particular, you can show easily that you cannot possibly approximate a traveling salesperson with any good constant factor in the general case, because you can always reduce to a Hamiltonian path. And there you don't need big weights. So in the general sense, traveling salesperson is relatively hopeless to get anything in terms of approximation guarantees. If you place this restriction on the distances, then we can do something. And maybe the intuition, why does the triangle inequality help us in any way? That might not be so obvious if you haven't thought about it a bit. Let me draw some example. And here, I'm just going to do an even more restricted special case, which is the Euclidean traveling salesperson problem, where the distances are the Euclidean distances of points in the plane. Now, of course, yeah, it's a complete graph, right? You always have all distances. So it gets a bit messy to draw. The big point, let me first say the big point about having triangle inequality means if I somehow have a solution that goes like this, it goes via some other city, but it turns out as part of my algorithm that it's inconvenient to have this detour in it. I can always instead shortcut it and take the direct edge, and this is never going to make the tour longer. Okay? Yeah, nobody can read that. Reduces the length of the tour. And you can easily come up with distances where that's not the case in the general sense. You need the triangle inequality for that. The special case that I'm drawing here, just as a side note, the Euclidean TSP is a subset of metric because the Euclidean distances obey the triangle inequality, but it's more special. And so in a way, just as kind of general knowledge, even though we're not going to get into this, if you know that the distances are Euclidean, you can do better than Christophidis' algorithm. In particular, there's a p-TAS even, so you can get arbitrarily good approximations, but then the time degrades with epsilon. But not so for metric. At least I think nothing's known. I don't know if this is proven. Okay. Because of this shortcutting, you can do a very simple first step, which is based on minimum spanning trees. So we start with our complete graph. It has these weights. All we know is that they obey the triangle inequality, which again, the key point of triangle inequality is that you can shortcut nodes and you're only going to make the tour better. So what we'll do is we'll find a spanning tree. I'm just going to make up one, say it looks like this, maybe like this, not completely degenerate. We compute this spanning tree, and now you're just going to walk outside around the spanning tree. That is a round trip, right? It may visit some vertices several times. It's certainly, okay, I should maybe give it, say we walk around this way. You can always do this in a tree, right? You can always walk around. Because this is a planar graph that's with a single face. And we're using each edge exactly twice. But it's not a valid traveling salesperson tour in general, because you're visiting this vertex several times. But you can always cut it out and say the tour is not going to be worse. So whenever you say you start arbitrarily here, then you walk around. So you go from here to here. The actual tour would go from this to this, and then it would want to go back here, but you're just going to shortcut. Then it would want to go back here, but you're going to shortcut to that vertex instead. Then you again follow the tour around the tree. Now here you would shortcut. Here you would backtrack, 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 so you're going to shortcut all the way back. That's the actual tour that you output. That's a valid TSP tour. And the trick is it's not going to be longer than the gray walking all around outside the tree tour, but it's only visiting every vertex once. And so I termed this the baby Christophidis because it's not the full algorithm, but you could do this. Technically, you could say I'm taking every edge of the tree, making it into two parallel edges. Then the graph is Eulerian, which means it has an Euler cycle. So every edge is used exactly once. Because now, whatever tree I'm starting with, if I double every edge, it's going to have even degree on every vertex, obviously. And then it has an Eulerian cycle. So you can just follow that Eulerian cycle, which is, if you think about it, is precisely what we did. It's the same thing. It makes it even more obvious that we double the weight of the minimum spanning tree by using every edge twice. And we use the same shortcutting trick as I just explained. Whenever you visit a vertex, or you're trying to visit a vertex another time, you skip it. And it turns out this is a 2 approximation, which is not hard to see. We've essentially shown this on the example. The tour we initially start with, the Eulerian tour, which is not a TSP tour, or not a Hamiltonian path cycle, has cost at most 2 times the minimum spanning tree cost. Okay. And shortcutting doesn't make that longer. And also, if you start from an arbitrary TSP tour, say the optimal one, and you remove any of the edges, then you get a spanning tree, which will just be a path. So that also means that the minimum spanning tree, which is not restricted to be a path, will have cost at most the cost of the optimal tour, even minus that edge. So the optimal TSP tour is essentially larger than the cost of the spanning tree. And our tour costs at most 2 times that. So if you put that together, we get a 2 approximation. Okay. That's already kind of is non-trivial to come up with this minimum spanning tree idea, but not many fancy algorithmic tricks have happened. We can go one step further. We can do a little improvement on this. And in particular, this Euler tour that we're using on the tree is a little wasteful in that we're doubling all the edges. Whereas if you think about some trees, say this tree, no, it's not a good example. Let's take the path. This is almost Eulerian by itself. You can, with well, for an Eulerian path, it already works. You can walk back here and then cycle. What's another less boring example, maybe? Oh, come on. Somehow I want to find out what this bug is that causes the cursor to vanish. Well, imagine some other tree with even degree apart from the leaves. Then you can also try to do an Euler tour that doesn't duplicate all the edges. You may duplicate some, you'll have to duplicate some edges, but not all of them. Oh, come on. Cool. Other parts of the approximation chapter so far. This last bit we've already covered. Let me point out that there was a typo on the slides. So the definition has to be a minimization problem so that delta is greater than 1. And it used to be maximization. There was really only one way to read the definitions so that they made sense. But certainly what was on the slides previously wasn't the right one. Okay, we even got the live stream back and hopefully some useful recording. I think we can go through the first bits there before we need a break. So let's continue straight on this smooth continuation. We'll stay in the realm of approximations, but with a few different techniques based on linear programs, as we've seen before. In the next unit, we'll stay with approximation algorithms, but we'll bring back this powerful tool we've looked at briefly before, namely linear programs, which turn out to be a very, very convenient ingredient to build approximation algorithms. I'll do a quick recap in case you forgot, and also to set the notation, which certainly people will forget over many weeks. And then we'll look at different ways you can use LPs for approximations. In particular, we'll also look at this duality theory of LPs that I left out last time. And this really comes to shine in this chapter. So just briefly to recap, we've talked about this at length in oh dear, what was it? Unit 6, something like that. A linear program, and here I've already given the standard form. We'll come back to why that is convenient. Is an optimization problem of this sort. You're trying to minimize some cost. You have variables, which can be any real number, but non-negative. You have n of these variables, and you have a linear cost function that gives each of the variables some coefficient. And you have a linear set of inequality constraints, where you can concisely write these m constraints in the matrix notation. If you forgot what these look like, here's what they mean unfolded. But we've dug through that back in the day. Yeah, terminology that we had also last time. So a feasible solution is just some values for x in this case that satisfies these two constraints, these inequalities. We call that CTX, this value, the objective function value. And then an optimal solution is one with minimal objective function value or minimal objective value. And we'll usually denote that with a little star. Here it's formulated to have integer coefficients in all the functions and constraints. You can generalize it to rational coefficients without much happening most of the time. We don't want to have arbitrary real numbers because we need to represent them exactly. Rational numbers is usually fine. You can multiply the constraints and the cost by the common denominator if needed. It will sometimes make a difference though. So it's important to keep in mind that you should say if the coefficients are restricted to integers or not. That was LPs. Here's an example. Some like an arbitrary example that doesn't have a specific meaning. Just to make it concrete, and you can work out that it has a certain optimal value at this point and optimal objective value 26. We also talked at length back then about the geometric view, polyhedra, and extreme points. You can show that an optimal solution is always an extreme point where some of these constraints are met with equality. Instead of the standard form that I've shown you, you can allow equality constraints. You can allow variables that are not just non-negative. You can do max instead of min. All these standard tricks to reformulate LPs we covered back then as well. But you can assume standard form for algorithms because you can transform. In general, such a program can be infeasible, meaning there's no value for x that satisfies all constraints simultaneously. Or it could be unbounded in the sense that you can improve this to infinity or minus infinity for minimization. But the interesting case that pops out from typical optimization problems is that it is finite, meaning there is some concrete finite optimal objective value. Okay, that's what I mentioned. If there's some optimal solution, if it's finite, then there is an extremal point that's optimum. And we can compute those in polynomial time. In practice, the simplex method, but in theory, the ellipsoid method is the one that's guaranteed to be polytime, worst case. You know all this from back then. Just to remind people. The last bit, also repetition. Integer linear programs are almost the same as what I've just shown, except that we have a constraint that things are natural numbers, integral, as opposed to just non-negative. And that somehow seems like a harmless change, but it makes the problem NP complete. Even so, the decision problem would be, is there a way to make the objective value better than the threshold? And so it makes a big difference in terms of how easy it is to solve the problems. But also you can put these in standard form using essentially the same tricks. Anything I forgot? Any questions on any doubts about LPs at this point? Okay. As I said, basically repetition. Now over to the new thing. In this section, we'll look at the first way to use LPs, namely by rounding these fractional solutions. But let me take a step back before we get to that. We usually think of hard optimization problems in this chapter. And it turns out that these integer linear programs, they're NP complete. So you can embed every possible NP problem somehow as an ILP. So in a way, if we find good techniques to work on ILPs, that's going to solve all problems. But yeah, usually we have to work a bit problem specific. But we'll keep that in mind, that it's potentially very powerful. The hard bit in approximation algorithms, or in the design of approximation algorithm, often is that you don't know how good the optimal solution is. And so having some way to bound the optimal solution, it cannot be better than some value, is super helpful. And there's an easy way to get that using the connection between ILPs and the LP relaxation. So the LP relaxation, I think I didn't have on the slides for the repetition, is just you take an ILP and you drop the integrality constraints, you replace them with just greater or equal 0. So the general approach could be you formulate your problem as an integer linear program, knowing that you're not going to solve this optimally in polynomial time. Then you just drop the integrality constraints, turn it into an LP, and you solve that one optimally, which we can do in poly time. So you get some optimal solution for this fractional one. And the cost that you get for the LP is going to bound the optimum cost of the original ILP, because you're only making the feasibility region bigger. You're allowing more solutions for X, so the cost cannot get worse. Now that's almost a cool algorithm, except that somehow we can't get a solution for the original problem in the general case. Like it's not obvious if there's a general approach for that. We somehow want to go back to a solution that's feasible for the original problem and not just the relaxed LP. Right? Okay. But what could we do? A simple version is it's non-integral numbers. Let's just round them. And of course, this is easier than it sounds, because by arbitrarily rounding, you're not usually going to get a feasible solution. But sometimes you can. Even if you can, what will come up again, what we discussed back then, is this notion of an integrality gap, which is the difference, or the ratio, I should say, between the optimal objective value of the LP and the ILP. That's going to be a barrier for how good this approach in total can be, because you're trying to get some solution for the fractional one to get it back to the ILP. So you have to do something there. I guess it's not clear if you necessarily have to have an approximation ratio. That's the integrality gap. Maybe you can do something smarter. All right, let's see this in concrete terms. And we'll return to our favorite set cover problem. Again, remember we have a ground set, and we have sets Sj that we want to pick some subset from. We have these S, still in dashed mode. The input was S, which is a collection of K subsets of this universe. We want to pick a subset of this collection of sets so that we have every element in the universe covered, so by one of the sets. And they have certain costs, so the goal is to minimize the cost. As an integer linear program, we can write this as xj, a variable that is 1 if the if this set Sj is part of the solution and 0 otherwise. Then this is going to get us the total cost of the cover we're picking. How do we enforce that it is a set cover? For every element in the universe, we sum over all the sets where this element is contained. That's this notation here, which we'll use a bunch in this chapter, so kind of memorize that one. V of E is the indices, so all the sets where E occurs. We sum over all those, and we require that at least one is 1. That's what the sum does if you restrict your numbers to integers. First of all, to have it in normal form, I wrote x is an integer or a natural number, but you can easily work out it never helps to make any of the entries of x bigger than 1. So an optimal solution will always be in 0, 1 to the k. That's the ILP. And you can relax that to a linear program if you just drop the integrality constraints and make it an x greater or equal 0. And for that, we can get a solution in polynomial time. And that's true in general. If we write the optimal objective value for the two problems with the subscript of the problem name, then the optimal value for the integral problem, it's the other way around, right? We're minimizing. So this is only going to be better than the integral problem. So we get a lower bound on the optimal solution. How do we make use of that? One option is to just round so conservatively that we're going to guarantee the solution is a feasible solution for the integral, for the integer linear program. And one way to do that is to take this frequency of any of the elements. So what's the largest number of sets that any element occurs in? That's what we call frequency. Then we take our optimal LP solution, some fractional solution, and we're going to pick all the sets where the variable is at least 1 over f. That's what I mean by round conservatively. We're rounding up way further, way earlier than we would normally think of rounding 0.5 up and everything else below rounding down. Here we're rounding up potentially much earlier if f is larger than 2. And so all of these we return, and that's our answer. Let's see how well this does. You can show it's an f approximation. We've seen that before, but still it's an entirely different algorithm. So I think it's kind of reassuring that we find the same approximation ratio. And remember, set cover generalizes vertex cover. So here I could even have written weighted vertex cover, where the vertices have some weight, not just counting the number of vertices. And there's a 2 approximation because in vertex cover, every edge occurs in exactly 2 neighborhoods or 2 incidence lists. Let's prove this quickly. We have 2 things to prove. First of all, that the algorithm even computes a valid set cover. And the second, the approximation ratio. To see that it's a set cover, take an arbitrary element from the universe. We have to show that it's covered in the solution. Now, we know that this x star, the optimal solution, it was feasible in the LP. And so in case you forgot, that's the LP, right? It's worth taking a picture. So it has to satisfy, in particular, this constraint for this specific E. So we have the empty sum is greater or equal 1. You're summing the values of these sets. Now, again, it's a fractional solution. So these could be any number between 0 and 1. You're never going to get larger numbers in an optimal solution. OK. Now we know that every element occurs, well, in exactly FE sets. That's how we defined it, but in at most F for the global frequency. So one of these, if that's going to be true for your xj star, one of those xj star has to be bigger than 1 over F because they're all non-negative. Right? Suppose they were all smaller, then you immediately get a violation of this. And so one of those at least is part of our output, and so E is covered. We could have several, right? All of them could have value 1 over f, and then we cover E many times. That's okay. How about the cost? So we have to show that whatever the algorithm here outputs is an f approximation. Now we're using, so far this was only using the feasibility of x star. Now we're using that it's an optimal solution of the LP, which means we have this CTX, the optimal solution of the LP problem. And that's a lower bound on the optimal solution for the integral problem. And for all the sets that we picked, we have this lower bound on the xj entry, 1 over f. Otherwise, we wouldn't have picked that set. So we can use that to just bound the cost. We take the cost of our set that we pick. It's the sum of all the sets that we included, sum of the cost of the sets we include. Each of these, I'm using this inequality and reversing it. So I'm solving for 1, if you like. Then you can insert f times xj star. That's using this part. Then the f goes out of the sum, and what I'm left with here. Oh. Not again. Ah. Guys, I'm gonna go home. This is horrible. No? It did. Amazing. In the next section, we'll look at a second way to use the fractional solution and round it somehow. And we bring back randomization here, which is yields different performance guarantees. I guess it's not obvious which one is stronger in general. The idea behind this is, especially if the values, like in our set cover case, are between 0 and 1, you could pretend they're probabilities. Or intuitively, if the fractional solution includes a set, gives a set a certain value, you could say this is a probability that you want to take that set. And so you can just do that. And the cool thing about that is that if you take the expected cost of the sets you get, of the collection you get, that'll be exactly the optimal fractionals objective value, just by definition. I guess assuming here that we have numbers between 0 and 1. And so that sounds maybe too good to be true, because we know we can't usually achieve the value of the LP. And indeed, most of the time, if you just randomly pick the collection like this, you're not going to get a feasible solution for the integral problem. But we'll see that you can often still get something out of this idea. And here, if you think in the context of set cover again, if some element in the universe occurs in a certain number of sets, then the probability that it is covered is 1 minus the probability that it is not. And the probability that it is not covered is the probability that for all the sets where it occurs, we don't pick that set, right? And that you can write, because we've picked the probabilities just to be these variables for the sets. It's 1 minus the product of 1 minus the variable. Now that sounds maybe not like you could do much, but you can bound it. Such a product is always minimized because it's kind of a convexity argument. It's minimized when you have the same value for all the xj's. And in particular here, because they're between 0 and 1, 1 over fe is, because you have the constraints from, so you're using convexity and the constraint that all these have to sum to at least 1. To bound it like this, then this is our seen that inequality many times before. This is in the limit goes to e, and for any finite value is below kind of the repeated interest thing. So you can lower bound the probability that a specific element is not covered if you just pick a random set cover candidate like this by at least some constant. It's not with high probability or anything, but it's also not zero. And so if you repeatedly draw such set cover candidates, this question turns into a kind of a coupon collector scenario. If you keep, the assumption is that you keep all the sets that you've ever chosen and just keep adding to your candidate set. Then if you do that for roughly log n repetitions, you should cover all the sets. Then you've collected all your coupons. And it's curious that this same harmonic number pops up. That term, if you remember, that was the approximation ratio of the greedy set cover algorithm. The reason to look at it again is that the methodology here is more general than set cover. So how can we make this work? In particular, we're using this randomized rounding from before and repeat it many times. So here R is the number of repetitions. So you see this is the outer loop, but we're computing one candidate set. So we do R iterations, but then for each of the iterations, we go through all the possible sets in our input and add this set with a certain probability to this candidate set Ci, and at the end we return their union. So any set that was picked in any of the R iterations is going to be part of the final solution. From this hand-wavy argument, maybe we should expect some logarithmic number of repetitions to be the right choice. And well, it turns out to get the numbers right, you want to use a slightly bigger number than that. So it's not ln n, it's ln n plus a constant. Right? And if you do that, then this algorithm produces a feasible set cover. That's indeed a set cover and deserves this name with probability at least 3/4. And we've done most of the work for the proof. The probability that a certain element is not covered was bounded by this 1/e. We've argued about the counter probability previously, but it's more convenient to write it like this, because this is the probability that a single element in the universe is not covered. To get a bound that none of the elements is not covered, we take the union bound over all of those elements. So the probability, this was for one iteration. If we keep repeating this R times, then we get the rth power of this, that it's not covered in all of the repetitions. So this goes down a lot with R. And the union bound then is that the result is not a set cover, it's just the factor n times this. So if you set R to natural log of 4n, this works out to exactly 1/4. Okay? Now this is the probability that we get any set cover. The other question is, how good will it be? And the expected cost is what we can bound. If we produce a set cover with this previous algorithm, then the expected cost it has is R times the optimal solution. So we essentially pay the same factor here. If that's the case, then this is only about the expected cost. We can, as always, use Markov's inequality to turn that into a success probability when we scale up the expectation a bit. So in particular, 4 times the expected size, the expected value will give you a probability of 1/4 to be above that. That's more what we're going to use on the next slide. But let's first prove this in the general sense. Our algorithm picks the final solution as the union of R repeatedly chosen things. These are all identically distributed and independent. For the cost, the cost of the final result is at most the sum of the cost of all those elements summed up. It'll probably be a bit less because we repeatedly draw some sets, but it's hard to analyze, so we'll just upper bound it generously. Then we use linearity of expectations and move that in. And because these are identical repetitions, each time the expectation is as we've calculated before, the optimal LP solution. So you get this R times as in the claim. Okay. Now this is not a randomized, this is not an approximation algorithm in the way we defined it, because it sometimes returns a solution that's not actually a solution. It's not even feasible. In this case, that's easy to fix by, if the algorithm fails, just taking all sets. So you run your randomized rounding. If the output is garbage, then you output all of the sets, otherwise you keep it. And with that, you can show that this is a randomized 4 log n approximation for set cover. We've basically done that, so you just have to prove that with probability 1/2, right? This was the definition. Randomized blah blah approximation means with probability 1/2, the approximation ratio is below this bound. And for that, we have to bound how often we return the entire set, because we cannot say much about its quality there. So the probability that C is not a set cover, which means we return something of bad quality, or that it is a set cover, but it actually is of poor quality itself in terms of the cost. That's the union of 2 events. I can upper bound that union bound by the sum of the probabilities. And both of these we've just bounded by the previous lemmas. So this was that the algorithm doesn't output a set cover. And this was the Markov inequality from the previous slide. So in total, with probability 1/2, we get something that's at least as good as that. And with probability 1, we get something feasible. All right. Yeah, that first, we can do the theory bit for that for sure. I want to make sure that we definitely finish tomorrow with all the core material. And then for next week, there's only the kind of fun bits that's not part of the exam. Only planning to use the Tuesday slot next week. We can use Wednesday if you want for some questions, or if people prefer to just prepare for exams, that's also fine. The thing I planned for next week, before I'm lost at the end here with the time, is a paper that was published at the conference, Fun with Algorithms. It's this cute optimization problem, and it has all of the components of this module. So it's a hard problem, but actually the exact complexity status is a tricky story itself. There's approximation algorithms. Okay, so there's randomization. There's randomization if you want, and there's FPT results known about things. So kind of fits too well for this module, but it's just for your entertainment. Is maybe not the right term for your for context or for your enrichment. Let's take it. Enrichment sounds good. So far, we've used LPs in essentially the way we've seen them in Unit 6 before. It's a way to make a hard problem easier by allowing solutions that don't actually solve the real problem, but they're not arbitrarily far away. They're fractional solutions. And so you can try to work from there. The real power of LPs for approximation algorithms comes via the duality theory. And so I'm going to try to convince you of that first in the abstract, and then we'll see examples tomorrow. what's this about? So let's again take a step back. Why did we use LPs for these optimization problems? Well, we wanted a lower bound. Say it's a minimization problem, just to fix the language. We could, from the relaxation, get a lower bound on the optimal solution for our problem by taking the fractional solution. Now, there's another technique to get that, namely dual problems, where you also get somehow a lower bound on the optimal objective function. It has some benefits, as you'll see later. Let's first see what this works like. And this I don't want to rush too much. Because I think is if you've seen it once the right way, you never need to remember the rules for dualization. So here's our fictitious LP from before. The goal is to somehow bound its objective value. So it's a minimization problem. We'd like to have a lower bound for how good can this possibly be. So we want a lower bound for this 7x1 plus x2 plus 5x3. But of course, subject to the constraints. Otherwise, it wouldn't be a solution. And so one option is we can take this objective function and we can make, because the x's are non-negative, we can make some of the coefficients smaller. That makes the overall value smaller. In particular, we can take, instead of 7, we can take x1. Instead of +1, we can take -1. And instead of 5, we can take 3. And then I've essentially reproduced this first constraint. So because x is feasible, this got to be bigger than 10. Ta-da! I've proven a lower bound on the optimal objective value subject to the constraints of 10. Right? All I've done is I've rewritten the objective function using the constraints. And what I've done here is I just lowered the coefficients for each of the variables from 7 to 1, from 1 to -1, from 5 to 3. Now I could try, let's try to make use of the second constraint, right? If that worked so well, maybe we get something better. And I could try to get to this. But it doesn't work for x2. So I can't really use that second constraint in the same way. Also, the lower bound we would get here is even weaker, so it's not interesting. But there's also kind of a hurdle here in using this trick. Now, what else could you do? These are inequalities, and inequalities can be added up. So if you add up those two, you get 6x1 plus x2 and 2x3. These are component-wise smaller than our bound here. So I can take the sum of the two constraints. Let's call this A and B. I'm doing A plus B. Then I get, what did I say, 6x1 plus x2, 2x3. And the sum of the right-hand sides is 16, which is better than my 10 from before. So I've made some progress. Aha, so how far can I push this? In general, I can multiply these entire constraints with some arbitrary numbers. I cannot just take the sum. I can take any linear combination, right? So I can multiply the left and right-hand side with some arbitrary value. Aha, but maybe not arbitrary because I have an inequality. So I certainly would want that my y's are non-negative, right? Okay. Also, to have a useful statement, I cannot produce this middle part where I'm making any of the coefficients larger for a lower bound. So I need to make sure, for example, for x1, I want to make sure that y1 plus 5y2 is below 7, right? Otherwise, I don't get this bound. And I get the same for the other two variables. So minus y1 plus 2y2 should be below 1. And for x3, I get this constraint with 3y1 minus y2 less or equal 5. And what's the lower bound I get from doing the linear combination? It's going to be 10y1 plus 6y2. And so I can pick any such y's, and I might as well pick the highest lower bound. That's the best I get. Okay? Is the process clear? And see how this, just by the numbers, nicely corresponds to working superficially on the LPs. The coefficients of the objective function here turn into the right-hand sides of the inequalities. The right-hand sides of the inequalities in the original problem turn into the coefficients of the objective function. If you've had inequality constraints here, that means that the multipliers you put to the inequalities have to be non-negative, otherwise you flip the sign. But had there been an equality here, you could have multiplied by a negative number, it would have been okay. And so you get constraints on the variables here come from the constraints in the original problem. And in a way, vice versa. If you have greater or equal here, then you can allow the coefficients to drop. If, say, x1 would have been allowed to be negative, then I can only get a valid bound if the coefficients are equal to 7. Okay? So you're playing a game where you try to get a lower bound for the objective function, and that game turns out to be another LP, and that's exactly the dual LP. I know that most or all of you will have seen dual LPs in some sort, but oftentimes it's just, here's the definition, deal with it. Whereas you can very, very logically derive all the rules for dualizing LPs that way. If you write them in standard form, then it's also quick to memorize if you prefer. If that was your original problem, the primal LP, then the dual will have this shape. Min turns into max. The coefficients here, they just swap and A gets transposed. And these are the generalization I mentioned on the example already. Okay? Now, so far, this was kind of by example shown what we're trying to do. This is just the definition of, if you start here, that's the dual problem. Whatever you prefer, you can show for any feasible solution in the primal, respectively dual, the pair of those, they always give you a bound for the optimal for the objective function values. Namely, for the minimization problem, you get a higher thing than for the maximization problem. If you imagine, oh, it's not bounded. So there's the values for the cost function. Then you have the CTX and BTY. They somehow lie here, and you always get that they're ordered this way. That's called weak duality, and it's a simple consequence of the definitions. You can prove it in general on this normal form as follows. If you take the dual constraint, A transposed Y less than C, transpose the inequalities. These are element-wise inequalities on a vector, so you can transpose that, and the inequalities couldn't care less, I guess. So C transpose is greater or equal A transpose Y, the whole thing transpose, and then, you know, the rules for transposition means you flip the product inside around, so it's YTA. And then you can just rewrite the objective value of the primal. Start from here, you replace C with that CT here. Then you have this associativity. You change the order of the parentheses. Then you use the primal constraint on AX, and that gives you a bound on of B here, and then that's a scalar. It's just a number. So if you take YTB or BTY, it's the same. That's weak duality. Okay, so you can always get this bound, and that's almost by definition. We've chosen the LPs so that this is the case. The more exciting part is that you can, for LPs, show that the exactly optimal values are the same, they coincide. Formally, if you have the some optimal solutions, X star and Y star for the primal and dual respectively, then the objective values match. That's a bit more linear algebra to prove, so I'm not too keen on doing it. We're just going to use this as a fact. And there's another cool thing that's useful for designing algorithms sometimes. This is a characterization of when a pair of solutions is optimal. Namely, so some feasible solution, X feasible for the primal, Y feasible for the dual, are jointly optimal if and only if these two conditions are true. So for every index j, either xj in the primal is at 0, so it's kind of tight on its non-negativity constraint, or the corresponding inequality in the jth constraint in the dual is tight. So here you have equality, and that's not helpful, I guess. You always have equality on one of those two constraints, either in the primal or in the dual, and you have this for all j and for all I. They're playing opposite roles. And they're called complementary slackness conditions because you cannot have slack in both of the constraints and be optimal. And in particular, this is an if and only if. All right. If you want to take the complexity angle, you can say for LPs, not interlinear programs. All of this is just for LPs, right? Not for the interlinear programs. For normal LPs, the fact that you have strong duality means that you have a yes and a no certificate, primal and dual variables. And so we know that the decision problem is in NP and in co-NP, but we already know it's in P, so maybe that's not so surprising. For the interlinear programs, much of what's on this current slide breaks down, but the weak duality you can still rescue. That stays valid, and you can dualize interlinear programs in just the same way, using the idea of lower bounding the objective value. I wonder if this is really simple. Maybe we can do this one actually in 2 minutes. Not much more. In the last section, I've shown you the LP duality theory. Let's have at least a quick example of how you can apply this in algorithms. And we'll look again at our friend's vertex cover. And we've seen the very first kind of approximation algorithm that we looked at was taking a maximal matching and just taking both endpoints, and that turned out to be a 2 approximation for vertex cover. It turns out there's a much nicer, deeper structure behind this idea. First of all, you can write down vertex cover and maximum matching, the overall largest in this case, both as interlinear programs. Right? Vertex cover, you have a variable for each vertex. You can either pick it or not, but you need to make sure every edge has at least one of the endpoints picked, so the sum of the endpoints must be at least 1. Whereas for matching, we have a variable for each edge. We try to pick as many as possible, but for every vertex, I can only pick in total value 1 on all its incident edges. And if you restrict that to integral variables, then it's exactly the notion of a matching. You could pick one of the edges of every vertex at most. So then that's exactly the 2 problems. Now, if we look at their LP relaxations, we see that they're duals of each other. And here's just by a concrete example to also make the structure extremely visible. It's a small graph with some 4 vertices, 5 edges. The problem for minimum vertex cover, the LP can be written like this. And so you have for each edge, you have a constraint, which says one of the endpoints has to be picked. But in LP language, just the sum of the endpoints has to be at least 1. And for maximum matching, you have a variable for each edge, and then you have a constraint for each vertex. For example, vertex B1 has E1, E2, E4, and so the matching constraint says their sum cannot be more than 1. And again, you can see from the structure they're exactly dual, or you make the game from before. If you look at the matrix A, which is the matrix of the constraints, then this is a bit inconvenient, but here the natural one is for the dual. If you look at this matrix, that's also known as the incidence matrix of the graph. You have the vertices as rows and the edges as columns, and you have a 1 if they're incident and a 0 otherwise. And so that turns exactly into the coefficient matrix for the constraints for matching. It's all not too deep or surprising. But the fact that these problems are dual means our lemma from earlier that the vertex cover is at least as big as a matching is just weak duality and nothing more. And it indeed works on the interlinear programs, not just on the linear programs. We'll look at this in a bit more general sense later. The last bit I wanted to mention here is this notion of a duality gap that we haven't had before. We've talked about integrality gaps. Duality gap would be, so you can have the integer feasible for the primal, and you can have integer feasible for the dual. And for the LPs, you know, that they match. There's no duality gap for LPs, but for the integral problems, there's a gap from going from all solutions to integer solutions in either of the 2 problems, and so there's also a gap when going from the integer linear program to the dual integer linear program. And that's what we call the duality gap. So that's the and of course we also have this guy here. That's the integrality gap that we've seen before. And for vertex cover and matching, a simple example, and we've seen this before, is that this duality gap is 2. In the worst case, it is at least 2, and it's also never more than 2. Okay, yeah. This we don't actually need, so it's just for, in bipartite graphs, it turns out the duality gap is gone, because you can always have the matrix you get is totally unimodular, so it always has an optimal integral solution even for the LP. And since that's true for both primal and dual problems, also the integral, the ILPs have to match, have to have the same optimal objective value. Let's declare that's just enrichment. Okay, see you tomorrow. Or later, rather.